My talk titled Explicit Finite Element Dynamic Earthquake Simulator for Sleep Behavior of Subduction Zone and Geometrically Complex Faults. So let's see. I try to get rid of something on the screen, make, let me see. Probably just go this way. Okay, and let's see. This is a talk outline, so I will briefly introduce our code that's explicit finite element code. We call it EQdyna. We developed it first for dynamic rupture simulation, and then recently we further developed it to solve the static problem using dynamic relaxation technique. And then after that, we further develop it into a dynamic earthquake simulator. We do this earthquake cycle simulation with spontaneous rupture simulation included in the cycle simulation. And then I show two kind of applications of this simulator. First of all, and some of my colleagues here know I'm a kind of a dynamic rupture modeler, and starting from my PhD about 20 years ago. And this is our code. So this code really not really fancy, but it's really based on the standard finite element for elastodynamic problem. And we know we solve this this equation of motion. And then we equation, we have a mass matrix and stiffness matrix here. We have also damping matrix here. And then we use a central differential time integration, which actually with diagonalize the mass matrix M here. This we don't need to really solve the coupled set of equations. So this is really a beauty of this kind of finite element method. You don't need to deal with those solver stuff, particularly for this large system of equations. But we know this kind of basic advantage also brings some disadvantage. So we need a really small time step to make sure the simulation is stable. The other point in the method is that we use 1 point quadrature element. This way will improve computational efficiency significantly, because if you do full integration in 3D, you need 8 integration points, but we just need 1 point integration. And associated with that, we need to deal with this called hourglass mode, which will cause instability. We have a method to control our hourglass mode. So overall, I think at the end, we solve the base acceleration at 1 time step by just directly divide the diagonal term of mass matrix by kind of a right-hand side of all the quantities, including force, body force vector, including due to the elastic response, including with hourglass control here. Okay, and we deal with, we try to simulate rupture propagation, dynamic rupture propagation. We need to characterize the fault in the mesh. So we basically use this traction and split node. Many of us use this, and basically we define the fault as a surface of split node, and we allow discontinuity in the displacement vector between split nodes, and we can deal with faults. Basically, that's shear fracture. We can also handle tensile opening fracture. Particularly recently, we know we talk about those geothermal hydrofraction stuff. Our code also trying to do some work on that topic. And after that, we know for the fault node, you have actual term here, that's traction between the split node. So this traction really control the behavior of this split node on the fault. So for the split node, you have this actual term on the right-hand force vector. And when many of us familiar with Steve Dace 2005 paper. And this is give you a scheme of sleep, the tracks and speed node method. And in our final element, we deal with really complex geometry. This is just show you one example about strike sleep nodes, thrust fault case. More details on the condition for faults. Deal with fault, we need a failure criteria. We know we have this Coulomb failure criteria, and this tau c that's with strength should be always limit. Larger or equal to the shear stress on the fault, and the tau c evolve with a friction coefficient and also possibly normal stress in pore pressure. And for the sliding case, so you have this equation to control shear stress evolution and slip rate evolution. So this is a equation from Steve 2005 paper. It's very looks simple but very elegant to deal with different situations of sleep and maybe stopping and the restart of sleep, this kind of different scenarios. And the friction coefficient we know evolve according to some law in our early code. We just use sleep weakening law, but later on we also implement real state friction law. And as we look at those 3D problem, we need to really take into account HPC resources. We try to parallel our code. So here shows some example in my group. Actually, those are work actually almost 10 years ago. At the time, we tried to really cooperating with computer scientists. We scale out. We parallel our code by using hybrid OpenMP and MPI. As shown by this diagram, we partition a whole finite element domain into many processes, and within each MPI processes, we use OpenMP parallelization. So this one shows a simple test, kind of a strong scaling, almost linear on the relatively small scale of the problem. And this table shows some kind of weak scaling at that time, about 10 years ago. When our code ran on the several hundred calls, like showing over here, pretty good scaling. You can see weak scaling almost similar, but when we at that time we scale it to 1,000, it's had some problem. But later on we improve it better, so we can scale it pretty good on the 1,000 of calls now. This is just show one example. I use this parallelized EQdyna to solve the rupture dynamics of this. Give one example of 2011 Tohoku earthquake with rupture propagation. Showing here is we know this is about the region of this earthquake. This is a fault plan projection. And the model shown here mainly try to explore a possible subducting Simon effect here labeled by D, and nucleation happened by E, this block. And given in this model, in this preferred model, rupture really can start beneath the cement and propagate laterally first, and gradually circulate around the cement, finally break the cement and make the rupture to the trench. And in another companion model, if this cement a little bit longer, also a little bit stronger in terms of static friction, actually this event will be just a smaller one, just limited to below the cement, magnitude maybe just about 7.8. Okay, and after I actually moved to Texas A&M, I tried to extend our dynamic simulation into multiple cycle. Basically, try to extend to the solve the quasi-static problem of earthquake cycles, basically between dynamic events. And here I just introduced one of the method we developed. This is really still stick with our EQdyna, that's dynamic solver, but we try to use dynamic solver to solve a static problem. We make use of this technique called dynamic relaxation. This method actually widely used in structural engineers. I think they use it to solve a static problem and based on dynamic solver. So advantage is that, similar as I mentioned earlier, we don't need to solve a large system of equations. This is really beauty. So we want to make use of this feature of this dynamic solver. And mainly, I introduced this damping term. This damping term here, basically, that's should be mass proportional damping with coefficient alpha here. The idea is that basically when the acceleration and velocity are damped to zero, your dynamic solution will converge to the static based solution of the displacement here, only kind of KU equal F. But this really need iteration. So typically in our work, we need either from a few tens to 200 iterations for each time step, for each kind of static problem. And the trick here is that how to select this damping coefficient alpha, and we follow this method called the adaptive DR method. It works pretty well. This is a kind of a verification of this using dynamic solver to solve a static problem. This is a classical earthquake cycle problem for the anti-plane fault. So this showing the result here. That line is from our simulation of our EQdyna-based solver, but for the quantitative problem at different time of interseismic period up to the whole period. So match pretty well with this analytic solution from Savage and Prescott paper. Okay, with that, we can develop this we call dynamic earthquake simulator. Basically, this is based on our EQdyna, and we do earthquake cycle simulation that captures spontaneous rupture propagation. The main thing we did actually, first of all, like I said earlier, we started with slip weakening law in our EQdyna, but the major challenge at the time, my student Bin Luo, really implement restate friction into our code with various forms of state evolution, including aging law, slip law. Recently, we mainly use this aging law, but we can also explore how slip law may affect the result in the future. And many of us familiar with this law. I don't spend much time. And we also need the base adaptive time stamping. We just follow with Nadia's proposed method, time step within the quasi-static process, really depending on the sliding velocity, also characteristic distance error here. This is a really diagram show we do our dynamic earthquake simulator really based on our dynamic solver. So this solver directly solves the dynamic process. And for other quasi-static process of earthquake cycle, we use really EQdyna with dynamic relaxation technique. So this is the example from that paper 2020. Show really this dynamic solver can capture this is suppose on a throttle fault interseismic process. This show color scale show the slip rate on the fault plan, and this is interseismic. You get the nucleation part. I suppose here doesn't change much in year. This is nucleation phase, and then you have dynamic event here with second in the time labeled here. After that, you have a post-seismic process here, and get into another interseismic process, and then finally you get to nucleation of the next event. Okay, I think most of us familiar with these two software. I call them actually earthquake simulator. And one by Nadia and her co-workers using boundary integral method, and very powerful, and including this method really can capture the co-seismic spontaneous rupture propagation similar to ours. But I suppose this method mainly limited to the simple faults, like showing this kind of diagram, planar vertical stress fault. The other well-known earthquake simulator, we all know that RSQSIM by Dietrich. And this is a simulator can apply to the complex fault system, like over here showing we know this South California one fault model, but this simulator does not capture the spontaneous rupture. And I would say probably most of us think earthquake simulator just like this type of cycle simulation without dynamic rupture. So that's the reason I call our method as dynamic earthquake simulator. So basically, our method is finite element based and capture the co-seismic rupture propagation and also apply to the complex fault system. Okay, now I try to present some example, particularly our recent work. I try to apply this dynamic earthquake simulator. As you can tell, it's relatively new. We published the first paper in 2020 on the method. So recently, my new student, PhD student, tried to apply it to mainly examine the sleep behavior of subduction zone. And we have two papers recently either published or kind of in press. First of all, we look at the tsunami earthquake generation. So many of us know we have this conceptual model from base observation and also from consideration of frictional property on the subduction surface. And I think this is a concept model proposed really this conditional stable part of subduction zone really host the tsunami earthquake, also slow slip events. So we use this dynamic earthquake simulator, try to examine this mechanism, how this works, and what kind of friction really control tsunami earthquake generation. And for the background, tsunami earthquake feature mainly including long duration and slow rupture propagation, also relatively lack of the high frequency radiation. And this is a relatively simple model on the subduction plane. And in this model, we have model parameter here. Mainly, you can see we have with this major fault area surrounded by creeping area on the fault, and this blue part, and then within here we have slip weakening patches as shown by A minus B, mainly below negative value. But within this zone, we have actually two asperities. One is with you can see over here, these two asperities has different properties in terms of normal stress level. On Z1, we have relatively high normal stress. We assume that's due to the subducting cement. On Z2 could have, has a typical normal stress, same as surrounding area. And we run a multiple cycle with dynamic rupture inside. On this model, as you shown here by slip rate evolution over the time by year, you can see we have some event, this slip rate logarithm up to almost zero, around zero, that's a dynamic event. And you can see we have event, some event ruptured both Z1, Z2, some event only ruptured Z2, that's a low, relatively weak strength of asperity. And we look at their rupture. Okay, I think this is just repeat some model parameter. We look at the two representative events. One is really rupture started from Z1, that's high strength asperity. This rupture time, this is sleep, this is the moment rate. And the main feature, I would say, rupture propagation, we can see we get this rupture propagation rate speed roughly about 1.9 for this event. And the second event only rupture the Z2 part and surrounding region. The rupture even slower, only 1.3. And okay, and we vary model parameter. If you separate this two asperity further away, doesn't really affect much of propagation. The propagation can still propagate through this conditional stable zone, break the other asperity, and with moment rate, we have two peaks. But the frictional property of conditional stable zone is really very critical. In this case, we reduce this A minus B from 0.02 negative to the point negative 2.001. Other things same, but the rupture only break the Z1, does not really break the Z2. So this is a comparison with observation in terms of the source duration, as we mentioned earlier. Tsunami earthquake, one important feature is the longer duration. So as shown over here from this observation, those tsunami earthquake, historical tsunami earthquakes have this kind of a normalized source duration because you have different magnitude you want to normalize into this case, normalize to magnitude 6 event, and then give you observed source duration for those historical events above about 9 seconds. So yeah, our model, we try to see what kind of a particular friction parameter on the conditional stable zone can produce this kind of a long duration. We find really with all other model parameter kept as constant, we vary A minus B within the conditional stable zone. We find really only very narrow range of A minus B for conditional stable zone can produce this long duration, like shown over here, only about 0.02 and or maybe 0.03, but either go to left or right, it cannot produce that long duration. And it's show really tsunami earthquake generation by frictional property, mainly within certain narrow range of frictional property. Yeah. So conclusion here, we would say one thing is about the conceptual model for about the conditional stable zone with asperity works well for the tsunami generation, tsunami earthquake generation, and like I said earlier, the level of velocity weakening of the conditional stable is critical to sustain rupture at a low speed, at slow speed. And we have different base asperity act differently. So for the high strength one, you can act as barrier in small event, also as asperity in large event. And this is one example. And another example is try to look at really interaction between the SSE, slow slip event, and megathrust earthquake. And for example, those observations show that suggest possible interaction between large event like Tohoku with slow slip event beforehand. This case, I think historically we have 2 tsunami earthquake over here, and we try to use this earthquake simulator with this is relatively a wide model compared to previous case, and we look at really we focus on interaction between slow slip event and megathrust event. So once again, similar model as previous study, but we focus on the interaction between SSE and megathrust events. Let's see, this is a similar model as previously case. This is a velocity evolution over the time. Once again, you can see there are many cycles. Some event ruptured both asperity, like over here, Z2 and Z1, and also Z2, Z1, but some event only rupture Z2. So we look at this time period from roughly 100 to 170, 100 a year into the simulation. And particularly, we find really before this event, event 2 ruptured both Z2, Z1, you have a lot of base SSE. That's basically this part. As there are 6. But before the next, next small event 1, you only have actually one SSE here. And let's see, this is a movie try to show that. This is really event 1. So ruptured both this is Z2 and also Z1, I suppose. Or only ruptured Z2. And now you have this SSE. Suppose this is interseismic, but SSE probably the second one, third one. Try to load this Z1 asperity. You have Z5. Also, you have S6, so those movement 6. So finally, nucleated rupture on the around Z2. This is event 2. So this rupture propagated toward Z1, but kind of a pause for almost 1 minute. finally, all the wave effect break this Z1, so make this event a larger one, so rupture the whole fault plan. And after that, you get into post-seismic and inter-seismic of 2, and you get another event. Probably good enough. And this is try to show some details of really those before the event 2, this SSE, 6 SSE mainly load the this high stress asperity. Each one load about a certain amount of stress into the interior of it. The cumulative effect is about 6 MPa shear stress is accumulated on S1. Finally, make the second event can rupture this S1. And this one try to talk about because of SSE event, this activity difference between 2 interseismic period, the coupling for this two interseismic period could be different. So this suggests really just based on the very short time period of GPS-based observation, trying to talk about the coupling and seismic hazard, may need to pay attention to this possible change of coupling over different cycles. Our conclusion here, probably very simple one, relatively different earthquake type may preceded by different type of activity of SSE. In our model, large earthquake really preceded by many SSE, and small earthquake preceded by relatively few SSE. Finally, I just briefly talk about our future work. We try to apply this dynamic earthquake simulator to study really multifold ruptures and over many earthquake cycles. In my group, we really did some work about in 2D. In 2D, like for example, our recent work in JGR, we try to integrate our model with paleo earthquake and paleo seismology observation, as many of you familiar with this part of fault and this paleo seismic study result. We did 2D modeling using our 2D version of EQdyna, but for the interseismic process, we really use a very simple viscoelastic model to analytically solve the stress evolution in terms of both shear stress and normal stress on the fault. So we do the many cycles. So this is a typical result in terms of slip distribution over the time along this fault system. So on the right, mainly showing you the typical event in many cycles. We find actually we can find some event like the 1857 that event, big one, also even 1812 event like event. So the dashed line shows the rupture time. So rupture started at 0 here, propagate bilaterally, and here ruptures are here. And also on the San Jacinto fault, you also this event really close to 1918 the events. Okay, finally, try to conclude with some remarks. So challenges. And 3D earthquake cycle simulation with a co-seismic dynamic rupture included are very challenging due to the large range of scales in both time and space. So time from seconds in terms of co-seismic and to 1,000 years of interseismic. And space, we know we need to solve the resolve the cohesive zone in dynamic rupture. That's about a meter scale, and then our subduction zone can have 1,000 kilometer long faults. And particularly if we integrate with observation for real case studies, require handling complexity model. For example, velocity structure, complex fault geometry. And our code developed by mainly use unstructured mass. So, but we can, so we use hydrohedral element mainly, but we with, if needed, we have degenerate wedge or tetrahedral element to deal with complexity. And the strategy, we need to further parallel, mainly scale our simulator into the tens of thousands of CPUs, implement GPU, also other emerging techniques in HPC. Also, we are currently our mass generation is really integrated in our solver. So this is good for the parallelization, but it's challenging to create a really complex mass with mainly hydrogen element. So we are working on this. And this is show one example. Our recent study, like our model size, roughly about 13 million elements. We use 600 CPU and memory about 300 gigabyte and runtime about 62 hours. Like the one example, and that's an example I just showed on the subduction studies. Okay, with that, I think I stop here. Thank you for your attention.